Hi everyone, this video is specifically made for Chem 3A and is regarding solving multi-step synthesis problems. The general outline of this video will be starting with explaining the structure of a synthesis problem, the general framework for solving these problems, followed by a simple example and then two fully worked examples. So a typical synthesis problem will generally take the form of a statement requesting you to create a synthetic scheme containing reagents and intermediates, but absolutely no mechanisms that lead from your starting material, which is pictured to the left of your synthetic arrow, to your product, which is to the right of your synthetic arrow. And your synthetic arrow will just have, or just look like a regular arrow, but with a dashed line instead of a solid line. Sometimes there will be certain constraints that your problem will give you, such as maybe your reagents can only contain 5 carbons or less, or something along those lines. So be sure to take that into consideration when you're creating your synthetic scheme. Now, when you're first starting your synthesis problem, there's a couple of things that you want to look at before you start making your synthetic scheme. My first tip would be to, 1, compare your starting material to your product. Most importantly, I would say you should count your carbons to see whether you'd need to add any carbons through your reagents. And something I found really helpful is to also circle functional groups that have either disappeared from the starting material or appeared in your product. Arguably the most important thing to be successful in synthesis problems is to really know each and every one of the reactions and mechanisms that you are learning in your classes. And this is going to include the type of stereochemistry that these reactions produce and any extra reagents that they require, or any other caveats that you should be paying attention to when considering these reactions and mechanisms. Lastly, you might want to employ a strategy called retrosynthetic analysis, which is essentially working backwards from your product to get to your starting material. Because if you start with your starting material, there's probably a million ways you can start and really not end up to your product in the most efficient manner. And also just a disclaimer, there really is no one systematic way to solve synthesis problems. Really the best way is to just know all of your reactions and their associated mechanisms and just practice applying them over and over again. So before we get started on the examples, I wanted to give credit to Professor Volhart. All of the questions used in this video will be from his past final exams, specifically either in the predict the product sections or the synthesis sections. So I just wanted to give credit to how I got all these problems. Okay, so this is sort of a simpler type of problem and one that you'd find in the predict your product section of the exam as opposed to the synthesis portion. As you can see, you're given the starting material and the product. We don't quite have a synthetic arrow this time, but above the arrow is 2 boxes, so that indicates that we have 2 steps in this reaction and we're only allowed to add 2 sets of reagents to go from starting material to product. So firsthand looking at this problem, we want to sort of employ those strategies we saw on 2 slides before. First, analyzing the starting material and the product and the differences between the two. So on first glance, we notice that we are going from an alkyne to an aldehyde, and that the starting material contains 8 carbons and our product contains 8 carbons. So we don't have to worry about adding any carbons via our reagents. The ring is unchanged, but the alkyne disappears and is replaced by an aldehyde. So again, what we want to do is sort of circle what we should be paying attention to. So our alkyne is changed to an aldehyde. Now we have to think back to our bank of reactions and mechanisms and sort of see if there's any direct way to go from an alkyne to an aldehyde in 2 steps. So why don't you pause this video and just sort of look through your notes, or maybe if you have all of them memorized already, just try to think of if there's any possible way to go directly from an alkyne to an aldehyde. Okay, so after giving it some thought, you should realize that there is no direct way to go from an alkyne to an aldehyde, and that instead we only know of the way to go from an alkyne to an alcohol. So let's start there and see if we know which reaction goes from an alkyne to an alcohol, and then from there, if we know of a way for an alcohol to be converted to an aldehyde. Okay, so after looking through your notes, hopefully you've realized that the mechanism of going from a alkyne to an alcohol is called hydroboration-oxidation, and when you're using an alkyne specifically, you need to use a reagent called dicyclohexylborane. So when we use dicyclohexylborane, that's the hydroboration part of hydroboration-oxidation. There's also an oxidation step which requires hydrogen peroxide and hydroxide ion in a separate step. So the result of the hydroboration would be an anti-Markovnikov and syn hydroboration. And then the result of the oxidation would give us our alcohol, which in this case is an enol. However, remembering our original problem, the final product was not an alcohol, but rather an aldehyde. So we have to think about a possible way to convert that alcohol to an aldehyde. And in the end, it ends up being a mechanism called tautomerization, which doesn't require any additional reagents, but will end up changing an enol form, which is pictured on the left-hand side here. Our enol form tautomerizes to the aldehyde, which was our initial desired product. So with that, our problem is solved, and we have the two reagents that may not necessarily lead to the aldehyde, but via an extra step that is sort of implicit in this problem, we achieve the desired product. Okay, so moving on to our fully worked example, which I'll call worked example number 2. This is a actual synthesis problem, so what you normally find in a synthesis portion of the exam. Here we're going, or here in this original question, the problem states that we are only allowed to use reagents that contain 4 carbons or less. So let's keep that in mind as we create our synthetic scheme. So again, just going through our thought process, we start with a 2-carbon hydrocarbon, which is unreactive, and we're changing to an aldehyde with a cyano group. So to reiterate, that's 2 carbons to 9 carbons. So we know that our carbons will need to be added via reagents. And we'll need to somehow go from a carbon-carbon single bond to a carbon-carbon triple bond, which if we sort of consult our bank of reactions, realize that this is typically, or this could be done through a bimolecular elimination followed by an acid-base reaction, but we'll cover that later. And then lastly, we'll need to figure out how to go from a cyano group, so this reaction, or this functional group right here rather, we'll need to add that to a carbon in the middle of the chain. So obviously this looks like a very involved problem, but we know that we should probably start with a single bond and transforming that into a triple bond somehow. And just sort of the reasoning behind this is because if you were to create a long hydrocarbon and just create the long carbon chain first, there's no selective way to create our triple bond wherever we want. So the first priority should be changing from a single bond to a triple bond. So let's start with that. Alright, so as we go from an alkane to an alkene and then eventually to an alkyne, we want to start with a process called radical halogenation to make our starting hydrocarbon reactive. In this case, you can use any halogen, but in this case we'll use Br2 and light to add a bromine to one of our carbons. That will set us up for the second step, in which we can add a strong base to force an E2 reaction and produce our alkene. Finally, to set us up to create our final alkyne, we want to first halogenate the alkene so that we'll end up with bromines on both carbons, which will then allow us to apply enough base for E2 to occur 4 times and create this sort of funny looking molecule, which is 2 carbons that are triple bonded to each other and 2 nucleophilic carbons on both sides. As we go through these problems, I do encourage you to pause the video and just ensure that you can sort of see how we get from one step to the next in terms of mechanisms. And this will just sort of ensure that you have a good understanding of all the mechanisms and reactions that your class requires, so that you'll be in good shape to start solving these problems on your own. Alright, so continuing with this problem, we have our nucleophilic alkyne, which sort of resembles the middle of our final product. And since they are nucleophiles, we can just sort of give it the electrophiles that we need to obtain the final product. And what we've seen on the left side of the final product, which I'll circle here, is a sort of 3-carbon substituent with not much else. So we can just involve a simple SN2 reaction with our favorite leaving group. So in this, or our favorite good leaving group. So in this case, we can just use iodine. And that SN2 will provide us with the exact left substituent that we've seen in the final product. For the right substituent of the final product, it's a little bit more complicated because we'll need to be able to eventually augment the first carbon to the right of our triple bond, and we'll need to be able to add a CN group. We don't have a very specific reaction that will allow us to immediately add on that CN, so for now let's just add an aldehyde, which is written as CHO, or you may see it written as CHO if it isn't written out explicitly as an aldehyde, and that will give us this alcohol, which we can then play around with to finally achieve our cyano group. So once that's done and we have both sides of the alkyne sort of looking like our final product, we can use what we know about changing OH, which is a poor leaving group on its own, into a good leaving group, so that we can finally just add our cyanonucleophile that will give us the final product. And we can use something, or we can use this reagent right here, CH3SO2Cl, which will make this OH into Cl, which as we know is a very good leaving group. And once that's done, all that's left, or all that's required, is just adding our nucleophile NaCN, and that will give us our final cyano group. So here's our overall synthetic scheme with the first overall step of changing our alkane into an alkyne, and then eventually adding the 2 substituents necessary to achieve our final product. Okay, so working example number 3 is a very similar problem. The only big difference would be that in the original problem states that we may only use reagents containing 5 carbons or less. So once again, going through our thought process, we notice that we are going from an alkene starting material to an alkane final product, with our alkane sporting many new substituents that were not initially in our alkene. Counting our carbons, we're going from 6 carbons in our starting material to 12 carbons in our final product, which indicates that we will need to add carbons in our reagents. But again, keep it under 5 carbons as the constraint in our original problem stated. So it looks like our original carbon skeleton is retained, as we can see that the isopropyl and the implicit H on this alkene are still present on our final product, and the same goes for our methyl group and its implicit hydrogen. The stereochemistry is retained. We will just need to figure out how to add a cyclopentane and an SCH3 group to the alkene. So let's sort of brainstorm ways we can add these substituents to the carbon, starting from an alkene and possible intermediates that we may need to go through. So pause the video and try to think before moving on to the next slide. Okay, so given that our stereochemistry has been preserved in our final product, we know that we'll need to use a syn addition to our alkene starting material in order to achieve the preserved stereochemistry we saw in the final product. And if you consult your reaction bank, you'll notice that what we need to use is called a peroxy acid, and when applied to an alkene will result in an intermediate called an epoxide. This epoxide preserves the stereochemistry found in the alkene. As you can see, the isopropyl and the H are still on the same side, in addition to the methyl group and its implicit H. Once that's done, we can just go ahead and add the two substituents that we need to both sides. So let's first start with a Grignard reagent to add our cyclopentane. And since it's rather large, it will selectively add to the less sterically hindered carbon, which in this case would be the side containing the methyl group and its implicit hydrogen, which will then lead us to this product right here, which has everything we need except for instead of this OH, we want a SCH3 group instead. So once again, as we saw in the last worked example, OH is still a terrible leaving group and we'll need to transform it into a good one. Once again, we can use the reagent we used last time, CH3SO2Cl, to transform this OH into Cl, a good leaving group. And then once that's done, all that's left is just adding our desired nucleophile, such as CH3S-, which will just do a good old-fashioned SN2 and add to our other carbon. And with that, we have our final product. So though the synthetic scheme was significantly shorter than the last worked example, it was still quite tricky because it required you to analyze the stereochemistry of the final product in order to determine whether you would need a syn addition or an anti-addition. However, once you figure that out, all you need to do is just add the necessary reagents for your syn addition, and then following that, just add the two substituents you require in your final product. And with that, I hope this video was really helpful and makes you feel more confident solving synthesis problems. If you'd like more PEACE content, you can check out our website, peace.berkeley.edu, where you'll find resources and articles that help you navigate your classes and your undergrad experience in general. If you'd like to access our one-on-one tutoring and advising services, you can fill out the form below and we'll get back to you shortly. And if you can, please like this video and subscribe to our YouTube channel for more instructional videos regarding a variety of subjects. Thanks so much for watching.